So there. So yeah, let's get started. Let's remember what we did last time. We talked about Gregor Mendel and his pea plants. We had a model. Well, he thought of the model like, okay, I grew 705 purple pea plant flowers out of 929 total. I think that nature probably is not using this many decimal places. There's probably really a 3/4 chance that there's going to end up with a purple flower on my pea plant. And yeah, he was able to, or we were able to test that model. Like, okay, what if it really was a 75% chance that you'd see purple flowers? What are the odds if you leave it to randomness and you grow 929 pea plants that you really saw a little bit more than 3/4 of those plants having purple flowers? So let's go back to the code from last time. Remember that you have access to this. And think about that. So what we did with him was, okay, we saw that this is what we got, this many percentage points, and we calculated a number based on how far away that was, 75.88% away from the model. It's like the 0.88% after multiplying by 100. So we did all that, and yeah, we made a distribution, 75-25. We drew from that 929 random pea plants, and we got proportions like, oh, okay, maybe it is not too bad. Okay, so that's where we went, and we calculated the distances every time we drew those random samples of pea plants. We repeated that test 10,000 times. We got all these distance numbers, and we wanted to see like how often was it the case that we saw a distance this far away, a little bit off, a little bit bigger than 75% purple flowers. And we noticed that, yeah, decently often that happened. So we were able to calculate a p-value, like how often was it that big or even bigger, which would make me think that maybe my model is wrong. Well, 54% of the time you'd see a value that big, even if you were drawing with perfect randomness. You're planting 929 perfectly random pea plants according to that distribution of 75% purple flowers, 25% white flowers. So yeah, we were able to do that. That's what p-values are. They're short for, it's not short for, it's just another word for observed significance level. And yeah, usually if you have a p-value that's less than or equal to 5%, people care. Okay? We also talked about the silly midterm example where like, oh no, section 3, something went wrong. We were able to find an average and notice it was a little low, but like if we drew a random sample of however many students were in that section, 27 students, we were able to see that, well, about 5% of the time, even due to randomness, you would end up with a poorly performing lab section with a score that low on average. That's interesting, but it's very close to the 5% cutoff, so maybe if you were the teacher, you'd say something different. So yeah, all that's from last time. Are there any questions about the code from last time or anything like that before we do very similar things? All right, so I stole a cool example from a website on the internet. Why does that not have the right color? So that's where we were. We stopped after that. And yeah, just have a bunch of examples, and I'm going to have you try a couple of them too. It might be shorter or longer depending on how much we do. But here is a silly, fun example of like all this in the real world. Like this was a real study. We are going to use their real data. So yeah, this was published in 2001. It was a study on fatty fish consumption and risk of prostate cancer in men. So interesting. Here's the blurb from the study. Like medical researchers, they followed this many Swedish men. So I guess they like to eat fish in Sweden. They followed them for 30 years. So it was a very long study to see if there was any kind of association between the amount of fish that they were eating, fatty fish apparently, and prostate cancer. And apparently they used twins in the study. Like they got nothing but twins, which is amazing. There's that many Swedish pairs of twins, which is really cool to think about. And that let them notice, like, okay, if one twin really didn't like fish and the other did, like there were no other really big factors. They had the same DNA, right? So that's kind of cool. And so they were able to study that there was a decent chance that you would get cancer more often if you did not eat fish. So maybe we should all be eating fish if we're men. Cool to think about. And so we can test that. We have the data. Let's get the data and take a look at that. I think it'll be fun. So I put that in the data folder. It's called fish-diet. If you'd like to get that yourself, but I'll do that for today. Fish diet. Maybe I should be eating more fish. All right, let's read it in. Diet equals, and this is kind of a disgusting looking table. We're gonna have to mess with it a little bit. Here's what it looks like. It's got as many rows as there were people, and it's just like diet is never means they never ate fish at all, and then cancer is yes, they ended up with prostate cancer at some point in their lives. And there's just a lot of these rows, and they're all kind of in a weird order. If we can see a piece of it if we take a little sample and be like diet dot sample 10 please. And so here's like some different values that you get to see, like a large amount of fish, a small amount of fish, a moderate amount of fish. And you also remember never. And then like, was there cancer or not? So cancer is going to be yes or no, and diet is going to be like large, small, moderate, and never, I believe, is all your options. So that's kind of what it looks like. And so we would like to get hard numbers. We'd like to count how many nevers there were, how many nevers got cancer, how many nevers didn't get cancer, for all these different categories. What should I be doing then if I want those numbers? What's the table operation that will give me access to that? Like bring together all the nevers and do stuff. Yeah, something like a group, potentially a pivot, depending on what you're trying to do. But I think a group would be a good one to start with. Yeah, it'd be like diet.group. And we will group by the diet column. Well, what do these people eat? So it looks like and by default, it gives you the counts after it groups them all together. So yes, it is. The only 4 differences are all these ones. Never ate fish, small amount of fish eaten, a moderate amount of fish eaten, and a large amount of fish eaten. And it looks like the Swedes, they do eat their fish. Most of them, like the majority of the people in this study, they had a small amount of fish eaten or a moderate amount. Some of them really liked it. Only some of them really didn't like fish, so I guess maybe it's a cultural thing. Like usually you're going to eat fish, so that's a small number. I don't know how useful that is, but apparently it's statistically significant still. And so we know that cancer is going to be yes or no. We can group by both of them, I guess, if we want to. Remember that there's a secret way to group by 2 things at once, like all the different pairs of values. So we've got diet and cancer. Those are our 2 categories. If you give to group, not a single thing, but a sequence of things, make array, or if I use the list here, it'll group by all the combinations of those distinct 2 or more things. So diet and cancer are the 2 column names, and it will just group by all the different ways that you could have different ones of those, and it will count the different ones. So that's kind of like pivot, but in 1 dimension, if you think about it. So that's something that group can do if you want it to do. It's a fancier way, but it looks like small amounts of fish and no cancer, that much. Small amounts of fish and they ended up getting cancer, that much. Okay. If they never ate fish, there are 110 of them who didn't get cancer, but 14 of them who did get cancer. You see how I'm reading that? Probably a pivot might be easier to look at, so we can pivot by both of them in some order, like diet.pivot. Because we got the 2 categorical things, that's kind of screaming pivot maybe. And so the first thing that you give to pivot is going to be what's on the x-axis, kind of, so it's going to go horizontally. We can do either cancer or diet, does not matter. Let's do it in alphabetical order, and then the next thing that you give is going to be the rows, going to be the y-axis kind of thing. So diet. So if we pivot by that, maybe this is a better one to look at. It's like, all right, if the men never ate fish, that means there were 124 of them total. 14 of them ended up with prostate cancer, and 110 ended up without it. So interesting to think about. So these are all our things. These are all our values. Probably it would make sense now to get some proportions, right? What's the percentage of men who never ate fish? What's the percentage chance that they got prostate cancer? Same with the small amount of fish eating men, stuff like that. I think that would be a good idea. And so I want to use the pivot table. I want to use columns from that particular table. Yeah. So let's call this something. Let's give it a name so I can use it and get columns out of it easily. So I'll call this pivot table, I don't know. The first one was diet. Let's call this diet 2 or something. I don't know. A little temporary table for us. And so what I kind of want to do is like, what's the proportion of yeses over the total, that's going to be diet 2 dot column yes, right, over the sum of the yes and the no's. So a bigger sum. The column value for yes over yeses plus the no's. Does that make sense? It's just going to give us a proportion. And it's going to go in the order that it was. Is that alphabetical order? I guess it is. So it looks like if you had a large amount of fish in your diet, there was like a 7.7% chance you ended up with prostate cancer. A moderate amount of fish looks to be the best deal. You get about 7% chance of prostate cancer. Never eating fish at all, 11.3% chance. That is a bit of a jump bigger. It's not a giant amount, but it is apparently a significant amount according to the study. And we'll test that. And yeah, if you ate fish, a small amount of fish, still you got the benefits. You got about a 7.7% chance of getting prostate cancer, just like the large amounts of fish. I don't know, maybe moderate is the answer. Everything in moderation. So yeah, I think that is useful. And I guess we want to test now, like, all right, what if, like, what happens, right? Is this real? Could it be just due to chance that the men who never ate fish at all ended up with a little bit more cancer just randomly? Because that's kind of what we want to know right now. Was this, like, did fish do anything? Was there a causation effect? So that kind of implies we need a null hypothesis that said something like what I just said, right? The null hypothesis is like, this difference that we see, there is a bit of a striking difference. It was just due to random chance. Okay, does that make sense? That's kind of what we're assuming, because we can simulate that. The cancer rate for men is some constant rate that does not depend on your fish consumption. Just like we saw that just due to random chance drawn from some other factor influenced this. No other factor. It was just randomness. Randomness is the reason that the people who never ate fish ended up with slightly more cancer. So that's what we can simulate. And now the question is, because remember what we did before, like we drew from, think about like the Mendel example. We had like a guess as to what the proportion was for purple plants. Do we have a good guess right now for like what is the proportion of men and just in general who are going to get prostate cancer? Maybe. It depends on what you want to think about. Because we have all this data, we could just sum up all the yeses and all the nos, couldn't we? That would be a sample of over everyone. I think that could work. We can use like the sample's total cancer rate, because that's just like everybody in total. If it was just random chance that you got cancer, and maybe that was the real rate. I think that's the rate that we could just test against. Maybe that could be something, but that does leave us wanting more. I would say there's a better place that we could go, and we might have time for that. But I think that's a decent proportion to deal with right now, if that makes sense. Like, what is like all the yeses over all the nos? Let's do diet 2 dot column. So what I'm doing now is the proportion of just everybody in the study who got cancer. Yes over, so like that's the yes column of the pivot table. Let's sum all the yeses up. So that's everybody, like how many cancer samples there were, over to like all the people in the study, which is, if you think about it, it's the diet table's number of rows. That's all the people in the study. Diet.num rows. So that is the proportion of everyone, like the cancer rate of everybody in the study. It is kind of small. So 7.4-ish%. Okay, so let's call that like the sample proportion. So that's a proportion of like everybody who's getting cancer from our sample. And so maybe our guess is that like due to randomness, where everybody has this chance of getting cancer, we saw that the men who never ate fish just randomly had a bit more cancer. What are the odds of that? Does that make sense, that question? Like that's what we could ask right now. What are the odds of that? And so we could do sample proportions now, because we have a sample proportion. Perfect. So what we want is to like generate a new sample of men right? Let's generate a new sample of men who never ate fish. How many were there in this study? We'll use the same amount, 124, right? And I could use this proportion, like this total proportion of cancer, to see like how often would it be, even if I was drawing from this kind of distribution, to see an 11.3% cancer rate. Does that make sense, that question? Like I came up with a proportion. Maybe there's a better one we could use, but like that's a sample proportion. Let's see how often it would be, sample proportions, the case that if I drew 110 plus 14 people, you just let Python do the work, from this sample, from this distribution. So you got to give it in some order. Like what's the probability that you get cancer? What's the probability that you don't get cancer? The proportion. So the first one is just the sample proportion. That's our 7.4%. And then they have to add up to 1. So the other one's just like the probability of you not getting cancer in the study, in the sample is just 1 minus the sample proportion. Does that make sense? How we could do that? And so this is me drawing 124 random people and with this proportion of cancer rate that we kind of guessed from our sample, and seeing how many of them ended up with cancer. And it looks like for this one, not a lot. Okay, not a lot, about 5% compared to our, where is it? 11.3%. If I run it again, of course, it's random. Okay, this time it's more 7.2% got cancer. Do it again. Ooh, this time we got 8% people with cancer. And so the question is, how often, if this was the real rate of you getting cancer, and just due to randomness, we were drawing people from using that, how often do we see a rate that large? Does that make sense? That's how we're testing our model. Our null hypothesis is that, how often is that the case? Because if our model matches that, if it is like decently likely to see a value that large, with even though this is the normal cancer rate for everybody, then maybe it was just a fluke. But if it's very unlikely, then that would mean that something else was afoot. Maybe there was a difference and we should all be eating more fish. Okay, so that is the question. That's the null hypothesis. And the alternative is like, okay, it wasn't just due to chance. The fish was the problem. The fish was the answer. Okay, so I want to like do this 10,000 times again. All right, so let's make a function that does and gives me back the proportion of men in my little random sample who got cancer, and that's going to be the first thing in the resulting array. All right, so it's going to be item 0 in the resulting array. So if we want to do this in one big line, just like that dot item 0. Does that make sense? Like that's the cancer rate in my sample of men who have never eaten fish before, according to this. All right, according to this distribution. If I rerun it, sometimes I get bigger values, sometimes I get smaller values, but they're going to be centered in theory around this proportion that we've come up with. All right, so yeah, any questions about that before I run the simulation 10,000 times to see if that is going to ever work out? See if we're ever going to get a value that big. See the vision? All right, so let's make a function. We've been calling it like do one thing, one sample rate of cancer. Let's do it like that. Where we return that big thing. So it's a very long function. It's just I'm copying and pasting that. I'm returning it though. So there's my function. And if I call it one sample rate, again, I get one new simulated group of 124 men, and we're seeing how often they got cancer, assuming that this was the rate at which they got cancer. Okay, just due to chance, it's different every time. Okay, so yeah, I think that is pretty much what we want. Let's do this 10,000 times. So where is my, I'll just copy and paste a loop from before. It's like, all right, simulations, 10,000 times, please. 10,000 of those. I've got, it's not sample averages anymore, it's like sample rates, I guess. So go that many times, sample rates get a little bigger with one sample rate each time. Does the loop make sense what I'm doing there? Just calling my new function 10,000 times, getting a new rate each time, putting it into the sample rates array that I started out empty. And it looks like, just staring at it, sometimes we do get a decent amount of cancer. Just due to that rate. That's interesting in itself. So maybe, I don't know, maybe the model's okay. Maybe it was just due to chance that that so many men were getting cancer. But obviously that is not true given the little blurb from the study. Significant difference. So let's notice that there was a significant difference. So all right, we can make a histogram, of course. So let's do that. We got to start with a table, right? Make a blank table, add the sample rates to that table with column, I'll call it rates, and I'll put sample rates there. Oops, not sample proportion, sample rates. So there's all my rates, and I can make a histogram then of that column called rates. Just histogram, column number 0. And it looks like, well, it's a big long table. Looks like that. And let's give it a bit more bins. Bins equals 20, let's say. And we're looking for about here, right? 0.11%-ish. Like how often, due to chance, did we get that? Or something bigger, right? Because if it was bigger, it would make us think that our model was wrong. That would be in the direction of too much cancer, and maybe the model's not good. So that's how we can calculate a p-value, right? We can see like how often was it so big, as big as we saw in the actual study, 11% or larger. Does that make sense? Because going in a larger direction, that would be like it's even farther away from the thing we think it is. So that would give us a p-value. How often, just due to random chance, was it that big, as big as we thought was too big, or even larger? Okay, so that we can go back to the sample rates array for that. How often was it bigger than or equal to this 11.112902? We'll just copy and paste it. That's the rate of cancer from the men in the study. And we can count how many times that happened, counting on 0. And so it looks like 480 times total, and we need to divide by how many times we did a simulation, right? How many times total out of all the samples we took. That's the length of the sample rates. Did we get a value that large? And it just so happens to be a little under 5% at the time. Just due to random chance, do we see a value that large? And so it is statistically significant difference. Does that make sense to us? It's a little hand wavy, but we ran a simulation. I think the one thing that maybe is not clear, like why it's a good one to start with, is this. Like, why use that particular number, that proportion to do our testing? It's kind of all we've got. Just assuming that there was one rate of all men for getting cancer, right? The best that we can get at to that rate, if there really was one, is just like take everybody in the study, because that's the people we knew who got cancer divided by how many people we had total. That's the most hand wavy thing there. But like that, starting with that, assuming that was the proportion at which just anybody gets cancer, we could run a simulation to see like, all right, according to that, how often would it be just by random chance that 124 people would get a bit more cancer than we would think? All right, and it looks like almost 5% of the time. So that's pretty unlikely, decently unlikely. So it is statistically significant, a statistically significant difference. Therefore, we should probably say that our null hypothesis is wrong, and there was a difference between men who ate fish. Okay? Any questions about what we just did there? It's a fun little example, I think. But again, we guessed a rate, and I don't know how if that makes us feel uneasy or not. So let's write that here. So we had to guess a cancer rate here to create a model, and that feels wrong to me. There's a better way. I promise there's a better way. We'll see that better way. The way that I would like to have done. We'll maybe do it again in the next chapter. A better way to do this kind of test in the next chapter. But we actually do have something that we could have done instead. We could have treated the cancer as a number. If you think about it, we could have treated it like a score, right? Like a midterm score. 0 if you didn't get cancer, 1 if you got cancer. And then we could apply the ideas from this midterm scores example, where we could draw a random lab section of 124 men, right? And get their average score. Does that make any sense at all? Like, we could have done it that way. And then we wouldn't have to guess something, would we? We wouldn't have to guess anything. We just like see how often getting a random sample of those men and getting their cancer rates, how often that was. We could treat it like a number if we had a number. There's a way to convert this categorical variable of cancer or no cancer into like a score. 100% score if you got cancer, 0% score if you didn't get cancer. So that's something we could do. You want to try? See if it's any different? See if it's more significant, less significant? Because you could do it that way. And that's kind of what the next chapter is kind of showing you in a different flavor. But I think that would be probably the better thing to do here anyway. So let's take this diet table and let's convert cancer from yeses and nos to ones and zeros. Let's get diet dot column. What are we doing now? Let's treat this like midterm. Let's try to treat this data set as like the midterm example, midterm scores example. So diet is that. If we get the column called cancer, that's a bunch of yeses and nos. I can turn those into ones and zeros by saying equal equals, like checking equality for yes. And then I get trues and falses, yes. Trues and falses, which for all intents and purposes are ones and zeros. Let's see, what's the best way to do that? We can put it right back into, I think. Let's try this. I haven't tried this before, but I think it might be possible. If I make a table with a new column called cancer and call it this kind of cancer, what does it look like? Oh, no, it does take the trues and falses, darn. In that case, I don't know. Let's make a function. Let's make a function that we can apply to this table. Good practice for the midterm. So let's say def cancer to number. Takes a cancer amount, yes or no, to a number. So like, I don't know. C for was yes or no. Like this is going to be yes or no. Call that variable yes or no that I'm getting. And so if yes or no was equal to yes, then I will return 1. And else, otherwise it was no, then I'll return 0. And this is a function that I could use on each piece of this table, cancer to number, because if I give it yes, it's going to give me a 1. If I give it no, it's going to give me a 0. Does that make sense? I'm using an if-else to do that. Any questions about those conditionals? We'll review those more on Monday. But I think that's a good way to turn this into a number. So we'll take now we say diet.apply, right? .apply this cancer to number function to the cancer column. And then I get a bunch of ones and zeros that I can shove right back into this table, all right? So let's call it diet.with a new column, cancer as number, I don't know, as a score, something like this. And then we'll put that right there. And then I got my ones and zeros. Boop. And then I can play the game that we played with the midterm. So diet is that. So let's call this, I don't know. I already had a diet 2. This is diet 3. Sure. But now I've got cancer as a number that I can take averages of with the ones and zeros. All right. And so now it's like a score, and I can do the midterm example stuff. I can select a random sample that is the same size as the men who got cancer, or sorry, the same size as the men who did not eat fish, 124 of them, and I can see how often, if like the null hypothesis is saying there's no difference, so I could have just as easily picked some of the other men to get cancer, right? To be in the didn't eat fish table. So I think that would work, because that's exactly kind of what we did for the midterm. It's like this one. It's like null hypothesis. The average score of section 3 is no different than a random section of people. For us now, the rate of getting cancer for our section 3 is men who didn't eat fish is no different from a random amount of just men in general. Does that make sense? So that's the way we could approach the problem again. And that could be our null hypothesis, and we do the same game that we did up here, where we take, like, let's get a random amount of people. So we'll sample with replacement equals false. We'll get a random, not a section anymore, but a random, I don't know, group of men. And it will be from diet 3 with replacement equals false. And it's going to be the size that we care about, which is 124, right? That's the one we've been using this whole time. 110 plus 14, that's 124. Boop. There's my random group. And sometimes they're going to get cancer, sometimes they're not going to get cancer. The idea is, like, I could have just randomly picked men if it was due to chance anyway. It didn't matter that they, like, what kind of fish they ate. So let's pick a few different people, and let's see how often they got cancer. So random group, what was their cancer rate? Just go and get the column for cancer as number, and then kind of take the average of that, right? Is that a thing? Or is it called mean? Cool. Ta-da! That's a nice, easy way to get another sample of men, because we're assuming that it didn't matter how much fish they ate, right? So under that model, let's just get a random sample of 124 men, see how many of them got cancer, just disregarding how much fish they ate, and seeing how often it would be the case that they got a decent amount of cancer like the original fish-eating men got. All right, does that idea make sense? So that could be our null hypothesis, and we can see how often this happens, how often they got like 11% cancer due to random chance. Again, at least this time we don't have to come up with some magical number that's like the true proportion of men getting cancer, because that is a little pie in the sky. Probably not going to happen very easily. But a sample proportion is decent. This is just another way of thinking about it. So let's do the same thing with our simulation. I will steal most of this code. What do we want to do? Let's get another sample rate. Again, I'll redefine the function one sample rate to do exactly what we just did this time. So, like, give me a random group of that many men. Give me how likely they got cancer by averaging the ones and zeros, right? That will be perfect. That will give me the rate. And if I do that 10,000 times now, and take a little histogram, that's going to probably take longer because it's dealing with table stuff now. Then I can do the same thing with a histogram. Cool. It still looks like 0.11 is over here. And then I can get my little p-value. How often was it what we saw for the original men, or bigger? Like, this is due to chance, right? Our model is due to chance right now, just like how many men happen to get this much cancer, how often. This is a bit smaller. So just like due to random chance, if it really didn't matter if you ate fish that you got cancer, given our sample stuff at least, and taking samples from that, it looks like there's about a 4% chance that just due to random chance, somebody who like ate some amount of fish or no fish at all got 11% cancer. Does that make sense? There's our p-value. And so that's very unlikely that predicted by the model. Because it's so unlikely, it leads us to think that there is a difference. Maybe it does matter whether you eat fish. All right? And so that is, I guess, the moral of the story. That's what the study showed. And so we should all be eating fatty fish, maybe. Any questions about what we did? I like this simulation better, I think. You have to come up with some random numbers. Like, think of it like a section in a class. Like we're taking some random people, seeing if it mattered or not. Seeing if one section really was special. And it looks like it was in this case. So yeah, that's that example. Any questions about any of this before I have you try some things? Of course, I'll do it with you, but I want to give you some time to think about it. All right, if we are good, here is a very nice question that we can ask now and test. I'm very excited for it. So the question is, were women more likely to survive the Titanic? So I think I want you to try this in detail. And the very first thing we need is like, what is going to be our null hypothesis here? So we need some model due to chance, right? Dealing with this question, what is your null hypothesis? Remember what that is. Whee! That's some chance model about how the data was generated that you can simulate. All right. So like for for Mendel, for example, our null hypothesis was just like, oh goodness, did I not write it down? Yeah. There was a 75% chance there was purple flowers and a 25% chance there were white flowers. That was the null hypothesis. And we tried to see if we could beat that down, and we could not. So same kind of thing you want to do here. What is the null hypothesis for women more likely to survive the Titanic than men? And I think, I don't know, do you guys want to try writing that down? Try guessing it first, thinking about it? And we can come up with a good null hypothesis so that we can all be testing the same thing. So yeah, maybe go to the written nice page and write down what is your null hypothesis there, remembering that like this is the one that we got for the last one. Whee! This is kind of what it looks like. It's kind of the opposite of what you want, maybe. So yeah, take a couple minutes to think about the null hypothesis in general. Hypothesis. It's very hard for me to say that word. And we will go from there. Let me know if you have any questions. It's a bit technical. Usually your null hypothesis is going to say something like, it's just in future ratings. We saw what we saw in future ratings. We turn that into a model set. Is that a cat or a dog? Mm-hmm. Mm. Yeah. That's the Lego version of the Titanic, by the way. It's probably giant. Was that enough time to think about the null hypothesis? Any questions about it before I show you what I think and look at your answers? Nice. Yeah. Something like that. There's just kind of like take the idea and negate it if you know about the idea of logical negation. Just like say no. Just kind of say no. Like they weren't more likely to survive the Titanic. The only difference that we saw, if there was a difference, like women happened to have been happened to survive more often. The proportion was larger. It was just due to random chance. Does that make sense? That's kind of how you throw that in. It's like there's no difference between the survival rates of men or women. They're not more likely. Independent. These are great words, great thoughts. I'm glad we're getting it. Nice. So yeah, that would be your null hypothesis. It's like no. Say the word no. So null hypothesis. That is not where the dot goes. So men were not more likely. Men and women, if women were not more likely, you could think about this in a couple different ways. Probably the best way would be to say that they were equally likely to survive. Does that make sense? That's the easiest model to come up with. No one was more likely than the other. Men and women were equally likely, because that's a great proportion you could use pretty easily to survive. And the difference that we saw in the real world example just happened to have been due to random chance. And the difference we saw I don't know, was due to random chance. So does that make sense how we can now simulate this model under the null hypothesis? Just like, all right, you've got a 50-50 chance of surviving, men and women. 50-50 chance of surviving. You can draw from that distribution to see how many men survived, how many women survived, given the total number of people. And then you can see how often it was the case that you got the proportion due to random chance that we actually saw in the real Titanic disaster. Does that idea make sense to us? You got to use the same numbers of the people that we used in the real world. But that's pretty much the start of it all. So thank you for your thoughts there. And so let's go there, Titanic. And I'll give you some time to try the next step. If you're already thinking about it, get started. But I'll read in the data, Titanic, and get myself ready for it as well. So there's the Titanic stuff. There it is. And we've got the sex column, right? Male and female. That's what you'll be using. You will probably want to do something there to get some ratios, okay? So probably the very first step you want to do is see how many, like what was the proportion of men to women who survived, right? Because you got the survived and the sex columns. You'll probably want to combine them in some way. So maybe the next step, and I'll give you a couple minutes to think about that. We'll just go in chunks. And then I'll eventually give you my answer after I have you try and ask questions about it. But like, I think the next step is probably to find the true rate that happened on the real Titanic. Like how many women survived? What was the proportion of survivors who were women? Does that make sense? Because that's what you're going to test your model against. Like how often was that the case due to random chance that you got that percentage women surviving? Okay. So how many women, how many of the survivors were women? There's a couple different proportions you could think about right now, and you'll have to think about like what's the right one. So try a few. Because you could pick out just the survivor and see how many were men versus women and take that proportion. Is that right? You could also take survivors and non-survivors total and see like out of all of the women who both survived and didn't survive, what was the proportion of them versus the men for the same idea, right? Men who survived versus men who didn't survive, what was that proportion? So what are we comparing against? Just kind of the next question. Get some numbers, see which one seems right to you. I'll give you another minute of a head start. All right. I think there's two ways to come up with this number, and I think one is the right way and one is the wrong way. So like there's what is it? There's Titanic dot where if you think about just the survivors, I feel like that's probably not the right one. Survived values are equal to 1. If you start with the survivors only and you count how many, like now group by sex, count how many were men and how many were women, I feel like that proportion is probably not the correct one. What's the best way to do that? Because that's like, I don't know, 233 over 233 plus 109. That's that proportion. It's like 68% of the survivors ended up being women. But you could also calculate a different proportion just of all the women, right? Start with all the women. Titanic, where the sex was woman. Remember the R equal to, you can just say, just omit it to get equal to. You can get that. Oh, sorry. Where? Oh, sorry. Female. Excuse me. And then you can get the survived column of that. I guess you could group by survived, I guess. And then you can get that proportion. That's 233 over 233 plus 81. And that's 74%. Which one seems like the right one? I think I kind of gave it away. What is the proportion of women who survive? Is it that one or is it that one? I think they're two different proportions that kind of could be argued to be that. Huh. Which one should we be using, maybe? We kind of want to think about our null hypothesis, I would say. It's like, all right, men and women were equally likely to survive, and the difference we see was due to random chance. So that means that if we pick some people, just like we play God and we forget about the survived column, just like pick some random people and see who survived or not, I think that kind of gives away the idea that you need to consider the ones who didn't survive as well. I think that's where my mind goes, and so I think that this second proportion is the correct proportion. It's like, all right, there were this many women total on the Titanic. How many of them survived? Does that make sense? Not, all right, among the survivors, how many of them happen to be women? That's a different question in my mind. All right. But again, you could argue it to be the proportion of women who survived. So I think the second one is the better proportion. All right, and I think that's the one we want to deal with. So I'll call that, let's call it something. This is like the sample proportion. That's what we saw in our sample, empirical thing. So that's the rate that we got. And we think, though, that was a fluke, yeah? So we're assuming under our null hypothesis that men and women were equally likely to survive, and the fact that 75-ish% of women survived was just due to random chance. It could have been a man or a woman on those lifeboats. They just happened to pick, due to random chance, women more often. Okay? Does that idea make sense to us? You see how you might simulate that? Any questions about it? Because I think that's the next step. All right? So that's step 2 for you. Simulate 10,000 like groups of how many women, I guess, is now the question, of 233 plus 81. You got to do the same amount of women who are on the Titanic, right? You have to sample from the exact same amount, like run a new sample Titanic. Simulate 10,000 groups of 233 plus 81, whatever that is, women, under the null hypothesis model. So that's where, right, where everybody is equally likely to survive. Maybe honestly, step 2 could be just like simulate a group, a brand new group. and we can do the 10,000 next. I think this could be step 2. Like simulate just one group of that many women, because it's got to be the same amount as there were on the Titanic, so we could run a similar kind of test under the model that we've come up with where men and women are equally likely to survive, and then get the proportion, right? And get the proportion of women survivors. Is it at all close to that? How often does it get to be 75% when it really is supposed to be a 50-50 split? Just due to random chance. Sometimes you will get that much, but that's like rolling 500 or flipping 500 coins and getting 400 heads or something. How often? Let's see. So yeah, does the question make sense? Does this step make sense to you? Like that's what you need to do next. Like just do it once and then you can repeat it. So I'll give you another couple minutes to try that. And again, ask me for help if you have any questions about anything. We are statisticians right now. We're data scientists. We're running a test. We're seeing if something was amiss, if there really was a difference between men and women. It was more likely that women survived. It wasn't just chance. That's all. That is our alternative. So that'll be a call to sample proportions. And you know the distribution now. That's great news. I'm going to stop my timer before it goes off. But were there any questions about how to set up the call to sample proportions? Does it make sense, like why we're doing it that way? So I would say something like this, probably sample proportions. I want exactly this many people, right? I want to simulate another Titanic with that many. This was how many women were on the Titanic, that many. And I want to see, under the assumption that men and women, there was a 50-50 chance of surviving. So that means the women as well had a 50-50 chance of surviving. That's an array where 0.5 and 0.5, right? That's your distribution. You could be like, the first one was survive, the second one was didn't survive, or the first one was didn't survive, the second one survived. It doesn't matter because they're both 50. There it is. There is my sample Titanic. And you can say like, okay, the first thing was the survivor percentage. Does that make sense? So like that's one sample Titanic under the assumption that men and women were equally likely to survive. And you can pretend that like the first one was the survivor percentage, the second one was the non-survivor percentage. So drawing from this distribution randomly, you're never going to get exactly 50-50. This is what we got that time. If you rerun it a few times, you'll see like, okay, we had more survivors than non-survivors, but you can just as easily have equal amounts, nice, or the flip. All right, and so now the question is, how often, just due to random chance, and it will happen if you do it enough times, will women's survivor rates get to be so large, it's like almost 75%, okay? Because that's, if it was due to random chance, then it should be pretty often that we get this, even with a 50-50 split. 50-50 split, all right? It's hard to talk today for some reason. So what we want to do then is simulate this a bunch of times. 10,000 is a decent number. You get a few decimal places, right, of precision when you calculate your p-values, but I think that's now step 3, all right? Step 3, make a function, that's what we've been doing, to to create a random sample and get the survivor rate, let's say, because that's what we're comparing against, survivor rate, the survivor rate, and then run that function 10,000 times to create an array. Run your function 10,000 times, saving the rate each time. And then we will see how often, right? We'll make a histogram after that, and we'll see how often it worked out. Okay, so that's going to be step 3, I would think. Make a function to do exactly that a bunch of times, and then do it 10,000 times, saving it into some array. Okay, questions about that one, that step? So just go back to what we did before. Copy and paste mostly. Run 10,000 simulations of, all right, under our model's assumption that men and women were equally likely to survive, take a sample of exactly as many women who were on the Titanic, get their survivor rate. So you're going to have to go in and get a piece of this resulting array, right? Just like we did before. So remember the operation that does that. Starts with an I. Yeah, this is fun. This is like, I have not calculated this p-value yet. We're going to see how often. We did make a choice, by the way. We could have done the same. We could play this exact same game with the male survivor percentage, because it's just one is the other. You could have thought about it that way. It's always so loud. All right. At least they're there. Yeah, let's do that. So I'm just going to cheat. I'm going to copy and paste 10,000 simulation. I'm going to steal all these functions from before because they're more or less the same. Yeah. So we've got, let's get, I guess it is a survivor. So I'll do one sample rate again. And so it's going to be that. Let's see. And we're going to return it. Return that, please. 10,000 simulations. There's my survivor rates. And I think that's it. Just like that's the difference. And so I got a bunch of sample rates again. And yeah, I think now, if you haven't already done it, step 4, do create a histogram of the rates. See how close, see how often you see this one, this amount right here, 74-ish%, right? Create a histogram of the rates, compare, and see how often, how likely it is to get a rate as high as we saw or higher, right? Because that would be in the direction of us thinking that there's something wrong with our model, right? As high as we saw or higher. And so that means for that second part, so also try to calculate a p-value after the histogram. So graphically, you'll be able to see something in the histogram. You'll see like, all right, is there 0.75-ish ever anywhere there due to random chance? Because like, look at these values. They're all hovering around 50, more or less 50%. So see how close you can get. And then if it's not obvious from the histogram, and it could be, honestly, try to also calculate a p-value. Like, all right, how often given our 10,000 simulations, did I see a value that was 0.74, whatever it was, or bigger? Because any bigger would mean that, oh, I don't trust my model even more now. That would be firepower towards your alternative hypothesis. It was even bigger, so we thought it was too big. Let me do that, Tom. $11.1, yes. This is exciting. This is like your first legitimate test you did all by yourself. So yeah, histogram and p-value. Let's see. I'll give you another 30 seconds head start. Right. Were there any questions? Were we able to get a histogram? Did 75% appear anywhere on that histogram? I'm excited to see it. Probably not, given what I'm seeing there. Probably not, honestly. Probably 0% chance. So that's fun in itself. So let's see here. I will be stealing whatever I did last time. 20 bends is probably fine. Boop. Alright, I mean, it got up to like 60%. So under a random chance of like you drawing a couple hundred people, it looks like you may get as many as almost like 60% survivors. If you do it 10,000 times. Obviously, if you do it infinitely many times, there is a chance that every woman survives under the model. Does that make sense to you? Like, randomness is randomness. It is possible that every woman survives or no woman survives in your random sample, but they're gonna, on average, hover around usually the rate that you've provided. So that's why you see that kind of curvy graph that's centered around 50%. If it is not clear that 75% is nowhere, we can compare our original proportion, this guy. I'll just copy and paste it and see how often it was our sample rates, right? Sample rates. Right, how often was it that or bigger? NP dot count non-zero. How many times in sample rates was it that or bigger? It was 0 times. And so you don't even need to divide by the length of sample rates, which was 10,000. There's a 0% chance that our model of men and women equally surviving predicts 75% women surviving. Does that make sense? So very statistically significant that more women survived. It was not just due to random chance. They chose to save the women and the children. So we have proved that beyond a shadow of a doubt, and that's really cool to think about. Are there any questions about this example? Do you see what we did? Did all the steps make sense? I think that's exciting, even though it is a bit of a morbid idea, but it is fun. So yeah, that was that one. Any questions about it before we have one more? Yes.
I guess I'm curious because the proportion of males survived to total males was 81%.
Oh, maybe we did do the wrong one then. I don't know. Males survive to total males. Let's look at that. 'Cause I sure didn't. I have not tried this one yet. So we could have done the other one, this other percent, 68, and we still would have gotten a similar idea. Maybe that one was the right one. I'm really not sure. It looks like where the sex was male, group by survived. So wait, what did you do?
Just hold the first step when we took the female survived divided by total females.
Yeah.
And we got the 74. If you do that for males, you get 81. At least that's what my computer.
I'm getting 23%. So if I take so where the sex was male, group by survived, 0 means they didn't survive, 406. Oh, did you do that? Okay, good. All is not lost. That would I don't know. I could have been wrong. I have not tried this example yet. So I think we did it right. So it looks like, yeah, there are only 109 out of 400, or even less actually, huh? Because you got added them up. Plus 109. Oh goodness. Oh, stop using that keyboard. There we go. Plus 109. Looks like the survivor rate of men was even less, 18%. Poor guys. Nice. Any other questions? This is fun stuff. All right. My last one for the day, I think we have just enough time to do a bit of it. I'll let you do more on your own, is let's go to the cereal data set, because I think it's fun, like the 1989 cereals or whatever. And let's first read the table. And then there's a fun test that we can do, I think, that we will enjoy. And it might be similar to maybe the midterm scores example one. So cereal, let's read that in. Look at all the cereals. So you got the ones that I'm going to care about are sugary cereals, like grams of sugar, I think. And then what shelf the cereal was on relative to the ground. So shelf 1 means it was on the bottom. Shelf 2 means it was just above that one. And then shelf 3 was on the top shelf. So you got all these cereals. And my question for us is, we could run a test to do this. Were the cereals on shelf 2 selected to be extra sugary because that's the height of a toddler's eye level? So that is my question for us. And the null hypothesis then would be just kind of say no, it was random chance, right? So the null hypothesis in this case would be no, shelf 2's high average sugar rate was just due to pure randomness. And so that kind of influences or implies what you could do to simulate, just like, all right, if it was due to randomness, then just go pick as many cereals as were on shelf 2, take a sample of all the cereals, make a new random shelf 2. Does that make sense? Make a bunch of random shelf 2s with the same amount of cereals on them and see how often you got a sugar rate that high. You see what I'm saying there? See how you could do that? So I think that would be the answer. And I think you could try it. So let's all get on the same page. Let's get the sugar rate. That will be well, actually, how about you try? Try to get the rates of how much sugar was on each shelf. So shelf 1, 2, and 3, they all have different things. And there's the sugars column that we care about. What was the average sugar amount for all the cereals on shelf 1, shelf 2, and shelf 3? Try to get that answer. And you can try to do the rest too, but I think that's the first step in my mind. So go get the average sugar rate for all the cereals on all the shelves. There's a table operation that you could do there if you combine it in the right way. So one average. I think that's a good one to average. Average sugar amount. Shelf 1 cereals, shelf 2 cereals, and shelf 3 cereals. Then we'll go on 3 shelves. Extra fiber. Does that happen? Really? It does. Yeah, stop the timer before it went off. So the magical operation is group, right? We want to group by the shelf. And then by default, you get the count, but we could use a different operation that combines stuff, right? We can use np.average to do the combination, to do the combinings of all the things. And we care about the sugars average. So what we could have done first was we could have extracted only the columns we cared about, right? We could have selected shelf and then sugars, because that would just give me this table, right, with only shelf label, shelf number, and sugars number for each cereal, and then it would give me what I care about all just in one place without anything extra. And look at the giant amount of sugar of all the cereals on average on shelf 2. It's 9.61905. That's quite a bit more than shelf 1 or shelf 3. Interesting. So yeah, I think now we can play the game that we did for, like, these are midterm sections, right? These are class sections, like the midterm example, where we can go and say, all right, according to our null hypothesis, it was just random chance that we picked the extra sugary cereals for shelf 2. We left it to random chance. And so what you'll want to do then is simulate picking a shelf 2 yourself randomly out of all the cereals you have. Okay, you're going to want to do it without replacement. Don't like duplicate cereals. That would be wrong. Got to use the same cereals, as many as there are. So the next step would be like, all right, how many cereals were on shelf 2? We need that. We need the count as well. So let's do it without the average. It looks like there were 21 cereals on shelf 2. So what you're going to do then is you're going to create, I think the first step would be just do it once. Make your one sample of, all right, pick from all these cereals, pick 21 of them randomly without replacing anything. So you can have separate things always, unique. Pick 21 random cereals to serve as your sample shelf 2 and see the average amount of sugar in that random sampled shelf. Does that make sense? Because if we're assuming that it was just due to random chance, then we should sometimes see a very high sugar value. Let's see how often we saw a value as high as we did. Okay, so try to do it once. Pick a random shelf of 21 cereals without replacement. So you're not going to duplicate cereals, because they didn't. And let's see what kind of sugar rate we're getting there. And then, of course, you can, if you want to do it ahead, you're going to make a function that's going to do that a bunch of times. Do it once, and you're going to do it a bunch, like 10,000 times. See the rates that you found. Sugar rates. All right. Does the idea make sense? Any questions about it before I show you my thoughts? It's going to be dot sample, serial dot sample. So I want a sample of 21 cereals. Like, just all right, if it was due to chance, give me 21 cereals. Then let's pick a random shelf 2 then. Serial dot sample. I want 21 of them with replacement equals false, so that we don't duplicate. Like, don't make them all Raisin Bran or something. So there's my sample of 21 cereals, and I just want to get their average sugar value, so I can say dot column sugars to get the column, and I can do np.average at the start, or there's like a dot average or dot mean. I can't remember which one. That one. So there's a random sample of 21 cereals. Apparently they got 6.66 grams on average of sugar. Whee. If I do it again, I get different amounts. Interesting, interesting. So yeah, the next step would be then turn this into a function. Do it 10,000 times. Get 10,000 sample shelf 2s and see how often we saw a sugar amount that was this high or higher. Yeah. If it was due just to randomness, then it should be pretty often that our model that's predicting sample shelves due to randomness would see that. How often? If it was very often, then the model's good. If it was not that often, 5% or less, let's say, then the model was bad and there was something influencing what was going on shelf 2, other than random change. I've not tried this one yet either, so I'm not sure what the answer is. All right, that was a good head start. Let me do it too. What do we want to call this? One sample. What is this? I guess it's a sample average. One sample average. Return that. So then I can do it a bunch of times. And you better believe I'm going to be lazy and copy and paste. 10,000 simulations. I don't want to call these sample rates anymore. They're sample averages. Sample averages equals that. One sample average. I think that'll do it. Oops. One sample average. So look at all my sample averages once it's finished. There they all are. Yay. And now we can make a little histogram. So a table with the sample averages in it. They're not called rates anymore. They're called averages. So I'll say averages. Sample averages is what goes in there. I'm sure 20 bens is fine. What do we got? Looks like the cutoff is about 9.5 grams of sugar. Interesting on average. So, bless you. I think that gives it away. All right. 9.61905 is what we saw on real shelf 2. How often does our model that's selecting just randomly, just assuming that's what's really happening, how often do we get that much sugar? So that's asking how many times in our sample, like our sample averages, how many times do we get something that is that big, equal to it, double equals to it, or bigger, right? Because bigger would be in the direction of, oh, the model's probably wrong, right? That's in the direction of I don't trust the model. That's even bigger than I expected it to be. So how often do we see that? NP dot count non-zero. that. Two times that happened. Over how many times you took a sample. Like, what's the proportion of times that our model predicted this, which is 10,000. You divide by simulations, or the length of sample averages, they're all 10,000. What is that in actual percentage lands? It's 0.02%. Yes? That is very, very statistically significant. Extra significant. It is so very unlikely that those cereals were chosen at random to go on that shelf, according to our test. Does that make sense? Like, we can say beyond a shadow of a doubt, it's very, very much the case that was not left to chance. There's a reason they put things on shelf 2 that were sugary. And that is fun to think about. So we've come so far, guys. We were able to ask questions and answer them and have like numbers to back up our answers right now. That's amazing. That's very powerful. This is data science. This is very cool. That's why I love this chapter so much, and we spent a lot of time on it. So I think that is the last example that I want to do today. Are there any questions about it or anything else? That was a fun one to end on. I didn't know what was going to happen, but it looks like yes, we can just not trust the supermarket. So yeah, there's that. I will assign due dates for homework 6 and lab 6 in that order after the midterm. So let's see. What do we got? I'll write down when I'm going to do it so that I don't forget. So the midterm is Wednesday of next week. We'll deal with that. So let's not have the next thing due on Wednesday. I think that would be evil. So how about we'll skip over to Friday for the first homework 6. Does that sound good? Homework 6 due next week Friday, and then we can do the Wednesday after that for lab 6. That seem reasonable? All right, let's at least start with that. If that's too much after the midterm, let me know. Homework 6 due the 10th, and then the 15th would be lab 6. So I'll write down to do that while you're working. You don't have to watch me change due dates. And then, question?
I was just wondering if you were doing the same week instead, if possible.
Let's see. It depends on what we're doing. I don't think that's a huge issue. You gotta speak up before I write it down next time.
Sorry.
Let's see. That should be fine. Wednesday and Friday?
Yeah.
I think I can manage that. Because, yeah, we're not going to finish another chapter until probably the Wednesday of that week. So that's not going to clash with anything. That will work. Yeah, let's do... So homework 6 due the Wednesday. That's the 15th. And then the 17th for lab 6. All right. Works for me. Yeah, so there's that, and then we are in about the middle of the semester, because like week 9 is for sure the middle of the semester. So what I like to do with my classes is to give out a little anonymous survey. If you would like to fill it out, I would appreciate your feedback. It's going to be completely anonymous. It's a little Google form that it's not going to trace anything back to you, but here's the kind of questions that I ask if you are interested in responding to any of them. You give me feedback about the class while you're still a student in it. So it'll help me for my future students as well as for the rest of this semester. If there's something that's going wrong, you can tell me. This is the first time I've taught this class, so I'm sure there's plenty of things that could go better. But yeah, please try to answer as many of these questions as you would like, in as much detail as you would like. I will look at your answers, and it will not be traced back to you at all. It's completely anonymous. So yeah, give me 3 things I should keep doing, stop doing, start doing. What would you like to change about this class, if anything? What have you liked so far? So yeah, I'd love to hear your feedback if you're interested in giving me some. This is not for a grade or anything, again, because I can't trace it back to you. But if you would like to give any feedback about the class, I would appreciate it. It will help me for my future semesters that I teach it, as well as the rest of this one. So yeah, I think that's all that I want to say. Remember that we got the midterm next week. It'll be here. I'll eventually release it. You'll come here, take them on the big computers, you'll click this little link, and then you're allowed to remember it'll kind of look like this at the start. You'll be able to click these links before you start the test. It'll be 90 minutes long though when you start it. and you can have these 3 tabs open in addition to the test, but no others. Okay? So yeah, remember that that's happening in a week, and I think that's everything. Any last questions about anything today? All right. So yeah, that's all that I've got.